Welcome everyone to episode 31 of Games with Go. Today we're going to do a bunch of quick cleanup and bug fixing, and then we're going to learn about Bresenham's line algorithm, and we're going to use that to put line of sight into our game so that we can't just see everywhere, see through walls, or see infinitely far. Alright, so for bug fixes, first thing is our little event system is not drawing strings properly. Instead of scrolling up when new events come in, they're just starting back up at the top and coming down again. So that's an easy fix. If we go to UI 2D, down into the draw function, the problem is we're using, we have this circular event buffer, and we're properly iterating through that. But then we're using I, which is the index into the circular buffer, to set our position to draw the string. And we should be drawing the string starting from the top and going down. So we just need to put in a count in here and use that count to do the drawing. And then increment the count each time through the loop. Now we should get the scrolling behavior we're after, and there it is. Cool, easy fix. Other quick thing we should do is the fonts should be scaled to the size of the screen. So if someone has a bigger monitor, the font should be bigger, or a bigger window. We want to try and make everything we draw scale with the screen as well as we can. So let's go to where we load the fonts. And for now, we're just going to do the small font. But instead of just making this 18, we want to make it a percentage of the screen size. So we'll use the width of the window for that. So we'll multiply times 0.015, see if that gives us a good size. That should be about 18 for the current window width we're using. And so the font's now going to be sized according to the window width. And then here we need to pick a size right here to make the Y position increment the correct amount as we go down our little event console. So there's a way you can do that with SDL TTF. You can ask how big a font is in a given dimension. So we can do this. So you can actually get the font size X and font size Y. We only want the Y. And we get our font, our small font. So UI font small, and ask for the size, UTF-8. And I'm just going to pick a letter here. Most letters are the same height, or nearly so. There can be exceptions to that. And then we can use that size here. And that'll just make our font scale automatically if we make our window bigger or smaller. And then last thing in here is the text is kind of up against the side of the screen and the bottom of the screen. It's kind of hard to read, so we're going to add a little bit of spacing. Adding some spacing on the left is real easy. We'll just start the rectangle at 5 instead of 0. And then to get a little spacing down below, we're just going to change this dimension a little bit. And that's a little nicer to read now. Okay, next up. So we fixed the event scrolling, made the font a percent of screen size, and added spacing and such to the event display. So that's all good. If there's any questions, fire away. I'll be checking in. Okay, so next up, make the events more descriptive. Let's actually start with this. So a while back we made this interface attackable so that we could send players or monsters to an attack function and use the same attack function. It was kind of bugging me. I felt like this was unnecessary complexity, and then I realized, in fact, it is. There's a much easier way to do this. So we're going to get to delete this entire interface and all the functions for it. Let's get to all go away. So just highlight it all and get rid of it. It's always nice to delete code. It makes your code simpler. So now we need to change the attack function. So what I wanted to do originally was have attack take in 2 characters. Because remember, the player and the monster both have a character struct embedded in them. So that's what I wanted to do, is just be able to send player and monster to the same attack function. And you just have to send the character field of the player and the character field of the monster. It's real easy. I just overlooked it. So let's rewrite attack to use the characters. Same logic. We take away an action point, figure out the attack power somehow. For now, we're just using strength. The second character gets its hit points subtracted by the attack power. Then we're going to go ahead and add the events in here. Previously, we were doing it in the move function, but that's going to change. So if the character being attacked is still alive, then we'll say add event, and we'll get their name and say they were attacked, say who they attacked, and we'll say how much damage they did. So we'll convert an integer to a string, and attack power is the damage they did. And if they're not alive anymore, do a different event. We'll say character 1 killed character 2. We'll need to import string conversion. And attack will need to take a level. It'll be a method on level. Okay, that's how attack's going to work now. So we've gotten to delete a lot of code, made that a lot simpler, which is wonderful. So previously we were doing the attack inside of move, and we're going to simplify this too. So we're going to yank all of this out of here. In fact, all move is going to do, for now anyway, is just change the player's position. And we're going to check to see if they can move there in a different function. We're going to call that, we're going to make a function called resolve movement to be a part of the level. It takes a position. And it's going to check to see if there's a monster there already. And if there is, that means we have to attack it. So here's how we're going to pass player and monster to attack now. So this will be level.player.character. It's that easy. Monster.character. And we have to use the ampersand because we're sending a pointer to a character. Did we specify that correctly in here? No, that should be pointer to character, so that when we change things, it actually changes whoever passed it in. We're not just changing a copy. And so we have to use the ampersand there because while we have a pointer to a player, we need actually the pointer to the character here. Okay. And then here we'll check to see if the monster died. And if so, delete it from the monster map. And we'll check to see if the player died. And if so, for now, we're just ending, panicking with a dead. Okay, so otherwise, if there are no monsters, we check to see if we can walk on that position. And if we can, and if we can't walk, we check to see if there's a door. Okay, and then as more features are added to the game, this is where we'll kind of do all the decisions about how to handle a movement command. If a player says they want to move here, what are we going to do? It's all going to be in here. And that lets us simplify our handle input function, because we have this like repeated logic we were doing here, if else 4 times. So we can yank all of that out. I'm going to yank search out for now because we're not actually doing that. And this just becomes resolve movement with the new position. All right, easy. Okay, then another thing we need to change with movement is we want, we've got the interface out of there. Events more descriptive, we just did some of that. Make monsters route around other monsters. So the reason they don't do that right now, let's get this working the way it is now first so that we can show the problem. We need to adjust monsters as well here. So we're not going to do any events in here anymore. So this needs to be monster.character and level.player.character. Oh, we gotta go to the level. All right. Imported and not used. Okay, so now we can see how much damage we're doing and how much damage is being done to us. Spider is currently doing 0 damage. Does that make sense? Is our spider weak? Yes, our spider is very weak. We'll give it some strength. Okay, so the problem is when monsters look for a route to the player, they assume they can just walk through any other monsters in front of them. But then when they actually try to make that movement and there is a monster there, they don't go anywhere. So what we want to make them do is when they look for a route, if there's a monster in the way, don't go that way. Find some other way. So we can see the behavior now. When there's a bunch of them, you see how those guys were just stuck. When I moved, nothing happened. When I move, those guys are still stuck. They should be trying to like go up and around or something, and they're not. So we need to change the logic for CanWalk to check for monsters being in the way. So if there's a wall or a closed door or a blank, we'll say false. We're going to get rid of this return true because we don't know yet if we're going to return true. We're going to check to see if there's a monster in the way. If there is, then we'll return false. If there's not, we'll return true. So this now we should see, yeah. So now we see the ones that would have been stuck before are now moving out and around and can start coming at me. So that's better movement logic. And that was me dying. So that's fine. All right, monsters move around. Excellent. Let's see. I want to take out this level.debug equals visited. That's what's making that plus sign when we start up. So that's gone now. Good. Okay, so now we need to make a change to get ready for the line of sight. Because right now our tiles are just a character, a rune. But we want to be able to mark tiles as being visible or visited so we can display them blacked out or faded out on the map. And to do that, we're going to need to turn this into a struct rather than just a rune. And we'll have to fix up all the places that use this to work properly. So it's still going to have a rune, but now it's also going to have visible Boolean. And it's probably eventually going to have a visited Boolean. So visited tiles will be ones that we can't see what's happening on them right now, but we know what they were, right? Like we knew if it was a wall or a room or something, but we don't know if there's a monster on it. Visible means we can see it and know what's happening on it right now. And we're just going to start with that. Okay, so a nice thing about statically typed languages like Go is when you make refactorings like this, the compiler tells you all the places that are screwed up. Whereas with a dynamic language, you would need to run the thing a bunch and test carefully or rely on unit tests to find these kinds of things. And they won't necessarily tell you the line of code. So this is a nice thing about statically typed languages. If you get sick of having to type the types all the time, this is when you save that time back again. Okay, so now these need to be runes instead of tiles. Go down to our next one. So now rather than switching on, okay, so then rather than setting the tile equal to blank, we set the tile's rune equal to blank. And the same all down the line. Remember, this is all just set up so we can use the Bresenham line algorithm to mark things as visible or not. Mark tiles as visible or not. So here we want if the tile's rune is equal to pending. Here we want to switch on the tile's rune, not the tile. Here we want to check the tile's rune. And we want to set the tile's rune. This is what opens a door. And current tile.rune. Let's see. So we're going to make a new tile. The dirt floor defaults to not visible. Same thing here. This is the code that figures out what tile should be under a monster, because we have a very basic editor, so it just has to figure out what's the closest floor tile, and I'll set myself to that. Okay, then in our UI, we're going to have some code that's broken by this too. Where were we here? Load texture index. Okay, previously we were casting the character we found in the file to a tile, but really we just want the character, so this should just be a rune now. And I think the texture index will just be mapping runes, the rune part of a tile, to a rectangle in the texture. Remember, this is what maps a character from our map into our sprite sheet. It's the rectangle for the correct sprite in the sprite sheet. All right, what's next? This should be rune. This should be tile.rune. Tile.rune. Now we don't have to do this cast at all. All right, I think that's it. Okay, great. Spiders killed us. Okay, so now we're ready for Bresenham's line algorithm. Fun stuff. So what we're using this for, if P is the player in the dungeon, and this is a wall, we want to be able to draw tiles that we can see differently than ones we can't see, right? So if there's a spider up here, S for spider, we should not be able to see it because there is a wall in our way. If there is a spider over here, we should be able to see it because the wall is not in our way. So one way we can figure that out is to draw lines sort of in every direction or many directions and just count the pixels along the line and keep marking those visible until we hit a wall or some distance. Maybe we have a limit on how far we can see, and then you stop. And then you can do the same thing in another direction. Here you start marking it visible, visible, then you hit a wall, and so then these tiles up here would not be visible. So you can't see the snake. So that's basically the approach we're going to take, is we're going to draw lines in a bunch of directions, and we'll iterate over those lines, each pixel, and see if we hit the snake, or see if we hit a wall that changes the visibility state. So we'll stay visible until we hit something that blocks the visibility. And we're going to use Bresenham's line algorithm to do that, to draw those lines. This was invented in the 1960s by Jack Bresenham. And back then it was used to actually draw lines on the screen to do graphics. And in fact, if you ever played Wolfenstein 3D or Doom, this is the sort of fundamental thing they're doing. They're drawing lots of Bresenham lines to draw those games. So it's very, very fast. Even back then, computers could draw a lot of them in a very short amount of time. And the basic idea is, say you want to draw this line right here on the screen. And so you look at it and you say, okay, it is mostly going in the positive X direction, right? It goes in the positive X direction faster than it goes in the positive Y direction. So we'll just start drawing pixels in the positive X direction, right? So this is a smooth line, but you can imagine if it was pixelated, it would look something like this. It would go a couple X pixels, then up one Y, and a couple X, right? Something like that, because it's more in the X direction than in the Y. So the basic approach for Bresenham is you just keep drawing pixels in the predominant direction, in this case positive X, but as you do, you keep track of an error value. And so every pixel you draw, you increment that error value. And once you cross some threshold, once that is greater than some threshold, then you increment your y value. That's when you go up, and then you subtract from your error value again, and then repeat the process. And you do that in such a way that you end up with the best, a good approximation of the line, and it goes very fast. Now the trick is that if you write the algorithm the naive way, it only works for one octant at a time. So it only would work for lines that go in the positive x direction and that are go to the right faster than they go up. A line that goes this way, we need a different variation of the algorithm. A line that goes this way, we need another one, and so on. So we end up with like 8 cases. But there's a way to kind of get around having to actually write 8 versions of it, which I will show. Oh, and I guess the other interesting thing here is it's very rare for people to use Bresenham's line algorithm to actually draw lines on the screen anymore, because people tend to draw polygons on the screen with GPUs instead. But it is common to use it to draw logical lines, which is what we were doing, right? We're using it to explore our space, to explore our map and learn things about it. So it's still a useful algorithm, even though we don't use it very often to actually draw pixels anymore. And that kind of thing comes up a lot. People might say you never have to actually write a sorting algorithm anymore because it's included, but weird cases come up where you do. Okay, so where should we put this thing? Now it's going to be part of our game, because remember, we're not using it to draw, so it's not part of the UI. It's just part of the logic to figure out what is visible. So we're going to take a start position and an end position for our line. So we'll kind of like draw a circle around the player. We'll pick points that are a constant distance around the player and draw lines from the player to each endpoint over and over. And this for now is going to return a slice of positions that represents the line. We're going to talk about an optimization we can do to make this more efficient. Because right here, anytime you see this make with a slice, it means you're allocating memory. And if you allocate memory, at some point the garbage collector is going to have to deal with deallocating it, and that has a cost. So avoid this if possible. And also slices that start at size 0 have to grow, and every time they grow, you have to throw away memory and allocate new memory, which is bad. Okay, so first we're going to figure out if the line is steep or not, which tells us if the line is going to be like on this side going mostly X, or if it's going to be going mostly Y. So we're just going to take the end Y minus the start Y, the absolute value of it, so the difference between the two Y values, see if that's greater than the difference between the two X values. So if the difference between the Y's is greater, then it's steep. And so if it's steep, this is how we get around having 8 different versions of the function. We just swap some values around. So we'll say temp is start X. So we swap the X and the Y. For both start and end. Okay, simple enough. And the other thing we need to check is if are we a line going this way or this way? And again, we will swap things around if we're going one direction. In this case, we swap the X's and Y's. Okay, so that sets it up so we can just write this algorithm one time and it'll work for all 8 octants. Okay, so first thing we want to figure out is the difference between our x values. And the difference between our y values. So delta x and delta y. And we don't have to do ABS on index because we've already swapped it around. We know index is going to be greater than start x. So we'll start our error at 0. And we'll start our y at start y. And if start y we need to make. So we're going to have a value for how far we're stepping in the y direction. And if the start y is greater than the end y, we reverse it. We do -1. Now we're going to loop from x equals start.x to x is less than end.x. And if we're steep, we're going to append. Because remember, if we're steep, we swap things around. So we're going to do position y comma x. Otherwise, xy. So we're taking our first x and y and just putting it in the list of results. And then we're going to increment the error by delta y. And if 2 times the error is greater than or equal to the delta x, then we increment by y step. Right, then we go up or down, depending on which way the line goes. And we subtract away delta x from the error. Okay, and that's it. So at this point, we should have the ability to draw lines. So let's give it a test. Let's see. Let's take, let's see. Let's make a key press maybe that will draw it. Maybe just draw it when we start up. So when we start up, so everything should be set up here. So let's use our start position wherever the player is. That'll be player.position. And we'll just make up some new XY. Let's see, we'll just do okay, let's make this a little simpler. P is equal to player.position. And this will be we'll just make a diagonal line up into the right or down into the right, five tiles. And then we'll iterate over each position in the line. And we'll set don't need the I. So we'll take our debug map and set each position equal to true, which should draw them in that red color, like we did for breadth first search. Oh, I missed a bunch of questions in chat. Let me go over them real quick. Line 132. Start x greater if start x equals. Did the line change? I think that's correct. Oh, no, you're right. You're right. That is not correct. Good catch. Thank you, chat. Someone's asking about Michael Abrash's Black Book of Graphics Programming. Yes, I read that when I was in high school. I didn't really understand it very much back then. But I did understand the line algorithm. I did draw some lines. And Peartreer mentions that there's a quicker way to swap with the positions. Let's give it a try. I like it. So is that the actual syntax? So start. Okay, well, I'll play with that later and see. I know there's some tricks you can do with tuples in some languages, so maybe there's a better syntax. Okay, back to testing. Let's see if it works. Okay, we did not draw a line. Let's print this line, see what it looks like. Oh, we're not even getting there because it's after the input check. Yeah. And we're not initializing our level.debug because I took that out erroneously. Where do we start? There we go, new game. Load level from files, probably where we're going to do it. Okay, so we're making a level.debug, make map position to tile. No, it's just Boolean. Okay, so yes, we're getting our line. That's where we were. Let's try a couple different directions to make sure. All right, that's going the other way. Good. All right, excellent. So basically what we want to do to figure out if things are visible or not is draw a bunch of these. After each turn, after the player moves, we'll draw a bunch of these, like in some radius. And start marking tiles as visible or not. So let's give the player, or perhaps characters, will have a sight range. Make that an int. So when we set up the player, we'll need to pick that. So we'll start out with 10. And our monsters will need one too. We'll just make everything 10 for now. Okay, so we'll start out just drawing a couple of directions. We'll draw like up, down, left, and right. So we'll need to do this in, let's see, handle input. Basically, every time we move, we'll need to change what we can see. So if we move, then we don't know anything about visibility anymore. So we'll want to say basically want to iterate over the entire map, I think. Yeah, so we'll want to iterate over the whole map. So we'll set tile.visible equals false. And then we'll draw our lines. So we'll get player position equals player dot position. Oh, okay, just do that. And then we'll do straight up. So and then iterate over all the positions of the line. Then we need something like our CanWalk function for CanSee. Because it could be different. You could imagine we have like a window at some point. And we could just make that a... No, it'll be the same way. It'll be taking a level and a position, return a Boolean. And for now, we don't need to check if it's in range. And otherwise it'll be the same. We won't check for monsters either. So we'll say you can like see through or around the monster. So this can have the default. Okay, so if we can see that position, if you can see through it, I guess we should make that more clear. It's a thing you can see through. Then we will set that tile visible equals true. Otherwise, we break out of the loop because nothing else is going to be visible once we're past that. Then in our UI, we need to not draw things that aren't visible. So when we're drawing tiles, oh, we need to make visible capital, or it won't be exported. Let's see if we can rename symbol successfully. So that's a Go plugin feature that hopefully, oh no, what have we done? Is it crashing or is it slow? I'm gonna close it. I can hear my CPU going. It's still going. It's chilling out now. All right, let's try that the old-fashioned way. Just follow the errors. Back to draw. Okay, good. And then for monsters, we don't want to draw them unless that's visible too. So if let's give it a try. We should only see just above us. Ooh, we see nothing. I guess it makes sense we shouldn't see until we move right now. Oh man, we're getting attacked in the darkness. That's scary. Where's our move function? There we go. So let's see what positions we were getting. Well, let's get rid of our debugging stuff here, because that's just going to add confusion. So it's only getting the tile the player is at. So is visible is maybe incorrect. Yeah, the monsters wouldn't be there already. Is visible, or can see through. Stone wall, closed door. Oh. It's going backwards. That's the problem. So our our line is probably sometimes going in reverse order because of the way we're swapping. Right, because of the swapping we're doing. So we're probably going to need to detect that and reverse this vector or iterate through it backwards. So that's probably something we'll work on next time. We got 5 more minutes. Let's see if we can do this better swapping syntax. So I think that is what we want. This would be n.x, n.y. And start.x. Wonder if this will work. It's a little different. Seems to be happy with it. All right, that is pretty handy. Cool. Gets the same incorrect answer. All right. Any questions before we log off today? Next time we're going to work on reversing the order when necessary so that we can count always from the player outward so that we can mark visibility correctly. Well, this dungeon is very dark now. We're going to get eaten by a grue, for sure. Yeah, well, we got eaten by a spider. Should have been a grue. We'll have to add those. Maybe it'll be stronger when it's dark. So chat is asking how we're going to pick the set of lines to check. Yeah, my plan is to draw a circle. So ultimately we'll, wherever the player is, we'll draw a circle, the radius of their sight distance, and we'll draw a line to each pixel in that logical circle. And that'll get us a good answer. It's not the most efficient way to do this, but it will still be very fast. You can go down a really deep rabbit hole for doing visibility, even in just 2D games like this. There's all sorts of interesting complex algorithms. You could even do things where you show partial visibility of a tile if you wanted to do like pixel perfect kind of stuff. We're going to start out just with drawing a bunch of lines because it'll work fine and it's relatively simple. All right, that is it for tonight. I'll see everyone Sunday, and we should be able to get this fully working on Sunday, and it'll be fun. All right, good night.